Hello and welcome to those vital few humans who have somehow managed to endure the first three webinars of reliability analysis, now what, and all that statistical and simulation gunk that we went through. And this is going to be the final lesson on how to make this happen. We're going to go through a brief review of what it is we're trying to achieve. And then some of the stuff we're going to look at today is actually making this work for real. So the first three webinars sort of set the scene and, amongst other things, describe the problem we were trying to solve. And now we're at the stage, webinar number 4, to make this a reality. So what are we trying to do? What we're trying to do is take data, and data is, in this context, is random data, because failure is a random process. This is all about reliability, but it can be applied to anything, any random process we're observing, and we have to make some sort of decision based on that, on the data we observe from that random process. So in this case, we're trying to make business-based decisions given our understanding of the nature of failure of something. So we know that failure is a random process. It's material imperfections, variation in manufacturing. There is seasonal weather changes. There are seasonal weather changes. And most importantly, perhaps, lots of different ways our users and customers use and abuse our thing. That's one of the biggest things that introduces variation. There's tons of other sources of variation that make failure a random process. So let's just say we have some data. Let's just go through the process of collecting our data from this random process. And here are some data points, which in this case represent the time to failure of something. It could be a consumer product. It could be an engine. It could be anything that is important for you to make the business decisions on. In this case, we are looking at a product which has a warranty period. Let's just say this is a wireless modem router, which has a 2-year warranty period. And we've done some testing, or got field data, and we have these data points. And we're trying to work out if we should launch the next generation of our wireless modem routers based on this data. And this is a problem that we often get faced as reliability engineers. We have a manager or a boss looking at us saying, are we good to go? Does the reliability as of now support us doing business option 1, business option 2, business option 3, launching, not launching, continue working on it, so on and so forth. And we need to be good at answering those questions. So we've got this data. In the first webinar, I went through the scenario we're talking about. We've got this data. We now need to help that boss come up with the right decision. And so what we're essentially doing is creating a system or a framework where data and stuff is put into the top of our meat grinder. Our meat grinder itself is what we call real analysis, not a statistical analysis based on tons of outdated assumptions. And what we get at the other end of our meat grinder is decision actionable information. That's what we're all about. So in this case, here is this decision actionable information for the reliability data we just looked at. We have, I urge you, if you haven't watched these series of webinars, go back to understand the scenario we're painting here. In this case, we have some reliability data, and to make the decision about whether we should launch or not, we have to come up with this decision actionable information. And what this is a distribution which summarizes our understanding of the profit we're going to make if we launch our product today. Now we can see that according to this curve here, there is a 40.73% chance that we will make a loss if we launch this product today. Why? Because there's a chance the reliability of our wireless modem router will be too low for the warranty costs to allow us to make a profit. But which means there's about a 60% chance we're going to make a profit. That might sound good or bad or indifferent, but another key metric we have from this is that we expect to make 32 cents profit for every single wireless modem router we sell. Now, without going into the details of what this means, this decision actionable information, this distribution of metrics that matter is the ultimate expression of information for our decision maker based on the data we've got. So what we want to do as reliability engineers, or engineers more broadly, is take those data points, put those data points through a meat grinder, and get this decision actionable information curve to help our decision maker make a risk-based decision. So this is what we're going to cover today in terms of the actual practical implementation of this meat grinder approach. But before we do that, we need to do a little bit of MCMC revision, which stands for Markov Chain Monte Carlo Simulation. Again, I'm not going to go through this in excruciating detail because webinar number 3 did that, but we're going to review what we talked about in the previous webinar, at least in a high level. Now, you might recall that one MCMC approach is a classic random walk algorithm. So why are we doing this? Well, because it comes down to that likelihood function. We're trying to understand the likelihood that certain models that we assume to be correct are actually correct. Now, if we assume a Weibull distribution, again, if this is all news to you, you need to go through our 3 previous webinars. This curve here represents the likelihood of potential parameter pairs that describe individual Weibull distributions. So this curve here is the likelihood function based on the data we have just gathered. Now, this looks great, this nice shiny surface, it's clearly smooth, it looks like it's fantastic, looks like a great summary of information about what we are observing. Problem is, we need a computer to generate this, but computers, they can't see this curve. This curve, which summarizes our understanding of the data we've seen, they can't see it. What we need to do is somehow create lots of little sample parameter pairs that represent the height of this curve for us to go and do all that meat grinding stuff. Now, one approach for creating that sample is this Markov Chain Monte Carlo simulation approach, which involves random walking. And we went through that last month, where essentially a computer is programmed to take random steps in certain directions. And there are certain rules that mean that if they take steps, if they choose to go in certain directions over others, the points will eventually coalesce in a way that mimics the density or the height of this likelihood function. There's lots of parameters at play when we're trying to create this walking behavior. So if we decide to do another random walk approach, you can see here there are much bigger steps. And sure, we are collecting samples. We are examining lots of different potential parameter pairs. But because the step size is so big, it's not what we call great coverage. So if we tune our random walk too far the other way, where each step size is too small, we never get to the hill that represents the most likely values. So we'll never get to the likelihood function if the step size is too small. So if we choose, let's say, an intermediate step size and allow the sampling to keep going, eventually we'll get enough points for us to be able to represent this hill, which computers can't see. And then that then allows us to use those sample data points for us to answer those questions, or provide the decision actionable information for a boss or manager to work out if we should launch our product or not. So this is one approach to Markov Chain Monte Carlo simulation. It's sort of the default approach, or de facto approach, because everyone in the field, when they first get introduced to Markov Chain Monte Carlo simulation, this random walking behavior is what people tend to think of first, or perhaps what people are taught first. I don't like it, and I'll show you why. Because there is another approach which we call slice sampling. So slice sampling is another Markov Chain Monte Carlo simulation approach, but it is, in my experience, a much better way of creating that representative set of viable distribution parameter pairs. So for example, we go back to our likelihood function. We select a point randomly, in this case, a point with a point described by a shape parameter value of 1.4 and a scale parameter value of 8. So what we're able to do now is essentially cut open our likelihood function and work out the height of the likelihood function at that randomly selected point. And then within that height range, the next step we do is then select another random point, which allows us to create a slice in our likelihood function. We just cut the top off at this randomly selected point. The next step is to randomly select a value within this now exposed slice. Now, it's quite hard to do when the slice is described by a weird, smooth polygon. So what we often do in the computer world is create a rectangle. And the rectangle is something that the computer can more easily randomly select points within. But sometimes we want it to be sure that our rectangle covers our likelihood function slice. We want to make that rectangle really, really big. Now, this is one of the criticisms of slice sampling, is that because we're randomly selecting from this big rectangle to make sure we cover our little slice, it's inefficient, which is true. It's a fair enough criticism. But the reality is most laptops today are orders of magnitude more powerful than the best computers that most statistical analysis experts had access to 10, 15 years ago. So the inefficiency of this approach is measured in milliseconds on your desktop. So it doesn't really matter anymore. And it's much better to take that inefficiency or so-called inefficiency to get a much better outcome as a result. And I'm going to talk about this inefficiency later on when I talk about what Chris does. That's right, I referred to myself in third person. So sometimes we want to make this rectangle big. We call this the rectangle of guess. We want to also make sure that our rectangle doesn't only partly cover our slice. This is bad. So our rectangle of guess needs to be big enough to cover our slice. And once we have our rectangle of guess, our computer can randomly select points, and it'll keep going until it gets one random point within our slice. And that becomes the next sample that joins all others for us to then go and create that big set of representative samples. And so when we do it for this likelihood function, the Markov chain Monte Carlo simulation looks like this. And straight away, you should be able to see it just looks like a much more uniform or much more, I suppose, representative spread of data points. And this is the same number of data points we used for that Markov chain Monte Carlo simulation example with the random walking. And we can compare the two as well. So looking from above, this is what our slice sampling gives us, but compared to our MCMC algorithm which is based on random walking, in this case, what we call the Metropolis Hastings algorithm, hopefully you can see that the the sample points we've got on the left through slice sampling, they just clearly look like a better coverage or better representation of that likelihood function which computers can't see. So before I go on, are there any questions about what we've just covered or what we've just reviewed, noting that there are whole webinars dedicated to what we've just looked at quite briefly, albeit in greater detail. Any questions at all? Not seeing anything. Okay, so with any luck, I'm speaking only to grizzled veterans who've gone through the first 3 webinars and are bored with me retelling the same story and now want to get into the next step. All right, so I see a question coming through. This is the same as the contour plots, right? Could you just clarify that question or statement a little bit further, Andre? This is the same as contour plots. Contour plots are obviously graphs which have lines that represent constant heights or constant likelihoods in this case. Thank you, Evan. So Andre, you're able to clarify your question or statement, maybe give a bit more context? Sorry, eta and beta plots. So are you saying, when you talk about eta and beta plots, which are the two parameters we're dealing with right now, when you say the plot, what are we plotting? What part of the eta and beta parameter set of characteristics are we plotting? You're talking about the likelihood of the joint likelihood of these parameter pairs given a data set? Okay, no worries. We'll have a chat after this, Andre. Mark, have you tested the difference many times, and is this distinction always the case, at least in your experience? Now, if you're referring, Mark, to the difference between slice sampling and Metropolis Hastings sampling, the answer in my experience is absolutely yes. With Metropolis Hastings, which is that random walk algorithm where you need to really work out what the right step sizes are, all those sorts of things. You need to have convergence criteria, as they call it. There's so much fine tuning that while it might be possible to get a Metropolis Hastings algorithm or random walk algorithm to be a pretty good way of generating these sampled parameter pairs, the amount of effort, dare I say it, skill and art that the data analyst needs to have to try and fine tune that the rules of this random walking is just sometimes very difficult to achieve. It's just not possible if you're going to be doing this sort of thing once every now and then, which is what most reliability engineers do. We don't do this every single day. So what we want is an approach which is going to work no matter what. So the random walking algorithms I find particularly problematic in this space. The slice sampling, in my experience, you're able to set a couple of basic parameters and it will tell you if there's a problem, which is always a good thing. But if we're in the business of being able to create this truly representative set of parameter pairs, and we're not going to be doing it every day, and we don't want to become Jedi masters at Markov chain Monte Carlo simulation, we just want to know enough to get the right results as and when we need it, then for me, it is hands down slice sampling every single time. So Paul also mentioned that Weibel++ has contour plots that look like this. And that's true. They do have contour plots, depending on, thank you, Mark. Depending on which version of Weibel++ you have, just be aware that Weibel++, even the more contemporary versions, which creates the contour plots, which are another way of representing the likelihood function. So I'll go back to one of the images of our likelihood function, if my computer lets me. So if we go back here, if you should see the slide now, which is that beautiful rendered image of the likelihood function of our beta and eta parameters based on our data set. Yes, Weibel++ can create a contour plot, which is another way of representing this, surface here, exactly the same thing. Problem with Weibel++ though, is it doesn't technically use this likelihood function to give you the confidence bounds that you need to have on your Weibel plotting. What I mean by that, subject from another webinar we've already done, but it actually creates a normal two-dimensional normal distribution, bell curve distribution, which sometimes closely matches this particular hill. Now, that is a problem because that approximation is never perfect. It's much better the more data you have. But when we were doing the when we were looking at this rotating likelihood, we could clearly see that it almost looked somewhat it looked like it had sort of three sides to it. This is clearly not a beautiful symmetric bell curve just in two dimensions. but Weibull++ always makes the assumption when it's calculating confidence bounds and things like that, that this can be approximated using a two-dimensional bell curve. And it's just not the case. So even though it's capable of producing those contour plots of likelihood, it doesn't use it for its calculations about confidence bounds. So just be aware of that. It's somewhat misleading, I would argue, but it has the ability to plot likelihood functions using contour plots, but then it doesn't use it to do the necessary mathematics, so necessary statistical analysis thereafter. Any further questions? Absolutely, Mark. All right. Any last questions? All right, so let's do this. So we're all up to speed now. The premise moving forward is that we're all up to speed with what we're talking about, at least philosophically. We've got data. We know what MCMC is. We now want to do something with that data using MCMC approaches to then create decision actionable information. So what we need to do when it comes to actually making our computers help us is follow these 7 steps. Put your data in, roughly estimate likely parameter values, create a log likelihood function. 4 is an optional one. If you want, you can find the MLE, what that means. We'll talk about what that means later on. 5 is create what we call slice sampling widths. 6 is then we sample, we run the algorithm. And 7, we use those data points, those sample data points to help inform decisions. So first step is put your data in. So we've obviously got data from somewhere, field data, test, whatever it is. We've collected certain numbers which represent the time to failure of our wireless modem router. And depending on which platform you're going to use, you just put your data into a matrix. So for those of you who use MATLAB and those of us who use R, you guys know how to do this. Get your numbers, put them into the memory of whatever application you're going to use to crunch these numbers. So that's putting our data in. Hopefully, we don't need to dwell too much on that. Get the numbers, put them in. The second thing we need to do is roughly estimate likely parameter values. Why? Because computers can't see that likelihood function. They don't know where it is. They're not like us. They don't. The surface has no meaning for them. They don't know what maximum likelihood means. We need to help them work out roughly where this hill sits on those axes. So we take our data, and for those of you who understand what Weibull plotting is all about, if we were to hypothetically plot this data on a Weibull plot, a very simple way of approximating our parameter values is to take the smallest time to failure, so the time to failure of our first device that we're testing, and our largest one, drawing a line between the two, which allows us, for those, again, who know what Weibull probability plotting is all about, to get a rough estimate of the scale parameter, and of course, a rough estimate of the shape parameter. So we know this is not perfect because all we want to do is get rough estimates of these 2 parameters get rough estimates of these 2 parameters to then allow our algorithms to keep going. Before I do that, I see a question from Michael. What informs the choice of the height? Do you mind clarifying that a bit further? The height of what, Michael? Waiting for sponsors to come through. The height of the slice. Okay, so the height of the slice for the slice sampling, I'm going to try and sidestep that question a little bit because that was the subject of the 3rd webinar. If there's any doubts or ongoing misunderstandings about what that slice sampling algorithm is going to do, I'm going to have to ask you to look at the 3rd webinar in your own time, just so we don't blow timings out for today. but the height of the slice is essentially part of the random selection of the next data point. It's been shown that that approach, if we follow that algorithm, we will end up with data points which represent the height of the likelihood function. So what governs the height of the slice is that iterative process that is the algorithm of the slice sampling algorithm, where you randomly select a point, work out the likelihood of that point, randomly select a height between the likelihood and 0, and where that new randomly selected likelihood occurs, that creates a slice. We then randomly select in the slice itself. Happy to talk at length after today's webinar, but before we do that, if there's any lingering questions, please go back to the third webinar, and hopefully that'll answer your question as well. All right. So what we're doing here is all we're trying to do is get rough estimates of our scale and shape parameters. And to actually make, while that's all well and good to look at on a Weibull probability plot, we don't want to do Weibull probability plots every single time. So here is the equation which gives us our first best guess at the shape parameter beta 0, where we're using what's called the median rank approximation of CDF. Again, if you have any questions about where the underlying mechanics for this equation come from, please feel free to reach out after. The point is we're trying to give our computer a starting point which is close to our hill, and this will do it. This is for the shape parameter, and this one here is for the scale parameter. And of course, these equations are in the handouts, so if you need to look at them later on, please feel free. But what this does is gives us a point which is close enough to our hill, our likelihood function hill, for our computer to do its thing. So the next step after that is to create a log likelihood function. Now, what's a log likelihood function? Well, the hill we just looked at, that surface, that represents the likelihood function, which is great. Problem with likelihood functions, at least computationally, is they're unstable. And why is that? Because a likelihood function is the product of individual likelihoods for each data point. Now, what that means is that the likelihood of a bunch of different data points can quite quickly go to infinity, or quite quickly go to 0. Now, when that goes to infinity or goes to 0, we lose everything. So we prefer to deal with the logarithm of the likelihood function, because instead of multiplying all these individual likelihoods, what we do is we add the logarithms of each likelihood function, which means we are less likely to tap out at infinity. And when I say infinity, infinity is simply a number that our computers think is too big that it can't possibly deal with, and so it then calls it infinity. Same with negative infinity, or same with very, very small numbers which are close to 0. So converting, moving from the likelihood space into the log likelihood space just makes everything a lot more stable on our computers. And virtually every algorithm that deals with Markov chain Monte Carlo simulation uses the log likelihood function. So how we create our log likelihood function for our data? Well, again, these are in the handouts, but we have to create a function where the inputs for that function are candidate beta and eta pairs, parameter pairs, which then allows us to use that data to give an estimate of the log likelihood of that set of data given eta and beta pairs. So on the left-hand side, we have the MATLAB code that allows this to happen. And on the right-hand side, we have the R code. This will create those two functions. These are different ways of creating the same log likelihood function, given that you put your data in. So again, this is in our handouts. And the next step is, if you want to, you can use that log likelihood function to find the maximum likelihood estimate. Now, this is an optional bit. All this does is make your starting point, which is close, as of right now, close to the hill, the very top of the hill. And it's just another way of, I suppose, making sure that we start our algorithms in the right spot. And sometimes people like knowing what the maximum likelihood estimate is of our parameter pairs. All this means is that you use an algorithm, there's tons out there, where you find the beta and eta pairs which maximize your log likelihood function value. It's an optional step, and because everyone should know how to maximize a function, I'm going to leave it right there. You can go away and research how to maximize functions in your own programming language if you need to. Once you've created your log likelihood function, it's just one way of really making sure that we're in the right zone for our likelihood function surface, I should say. All right, so the next step is create what we call slice sampling widths. Now, going back to our rectangle of guess. Remember, computers aren't really good at finding random points within a weird, smooth, roundy surface, or round shape, sorry. So what we do is create a rectangle, which we hope will engulf our slice. We can select random values within that rectangle and keep going until a value falls within our slice. Stop it there and move on to the next step. So this is our rectangle of guess. So how big should this rectangle be? Well, one characteristic of the algorithms I'm going to show you today is they try and speed things up by starting with a big rectangle of guess and slowly making it smaller and hopefully collapsing it around the slice we have selected. So for example, if the first randomly selected parameter pairs are over here, the algorithms we're going to talk about today actually shrink our rectangle of guess if that randomly selected data point falls outside of our slice. And if the next data point that is randomly selected is over here, then we decrease our rectangle of guess further, which means that a computer doesn't have to sample as big a space, which further means that we're more likely to quickly find a random variable value within that slice. Now, when I started doing this, I essentially created rectangles, really big rectangles, which are about 3 times the size of our initial parameter rough guesses. So that makes really big rectangles, but there is a problem with this as well. So let's just say that we randomly select points, but for whatever reason, the next randomly selected point is over here, sort of not in the slice itself, but sort of within at least one axis width of our slice. And when our algorithms then collapse what they call this hyperrectangle, there is a chance that this newly formed hyperrectangle is going to miss at least some of our slice. So this is a problem with most algorithms, including the ones I'm going to show you how to use today. But how do I fix this? And that's right, I'm going to refer to myself in third person. It's a Tuesday, so why not? I have my own approach where before I start doing this, I have my likelihood function and I ask my computer to come up with its own set of rectangles for varying relative heights of my likelihood function. It looks like this. And what that means is that my computer is now able to not have to worry about big rectangles of guesses. That we're able to really use these rectangles that we've already worked out, which match or contain precisely the entire slices we give for certain likelihood function values. And that means we not only speed up the algorithm a lot, but we virtually guarantee that there is no inadvertent missing of certain slices during our algorithmic approach. Now, there will be some cases where my initial set of rectangles don't cover all randomly selected points. You can see here, there's a couple which appear to be outside the biggest rectangle, which represents the lowest likelihood function, the lower likelihood function values. What my algorithm does is when this happens, it creates another contour beneath the lowest stored contour height, creates a new rectangle and allows it to keep going. So when I do this, it makes it so much faster And it also guarantees that we are not going to miss any part of our slice. The reason why we can do this is because in reliability engineering, we have really well-behaved likelihood functions. What does that mean? We don't, when we're doing data analysis, we can show statistically that the likelihood functions for pretty much every model we're going to use, Weibull, normal, log normal, what have you, will result in a single hill on our surface when we plot it in a 3D way, which means that we can do things that in this space that we can't do for general Markov chain Monte Carlo simulation algorithms, because they need to deal with scenarios which have 7, 8 different parameters. It might have multiple hills, might have saddles, it might have weird shapes. Reliability engineering, we know the likelihood function will be well behaved. It will be a single hill that's a single hill around a single point estimate, which is the maximum likelihood estimate. And we can create these rectangles from the start, which guarantee that we will get a good coverage. So that's how I do it. All right, so what's the next step? Now we need to sample. So in MATLAB, there is a code that we need to type in to make this happen. You can see that I have the inputs to my slice sample function, the best guesses for eta and beta. 10,000 is the number of samples I want in this case. I have, because we're dealing with a log likelihood function, the next parameter needs to be a log PDF, and then there's my log likelihood function, log L. The width is simply 3 times my best guesses for eta and beta. In the R space, on the right-hand side of this slide, R is not the same application that MATLAB is. It's obviously free to use, and so it doesn't have a suite of inbuilt functions and algorithms. So here is an example Markov chain Monte Carlo simulation algorithm from the Diversity package, which you should be able to easily find online if you do a bit of a search. But I don't want to advocate for one over another. And the problem with each different package is you can't really guarantee in the same way that you can with MATLAB that there are no underlying issues with the approach. That said, this Diversity is pretty robust, and the algorithm it uses is exactly the same as the algorithm that MATLAB uses as well. So find your own, do your own research. I'm not going to advocate for one over the other, but they're out there. And what you'll get is a bunch of parameter samples like this. So each row in this matrix is a pair of parameters which define a particular Weibull distribution. So this first column contains the scale parameters, and this column over here contains the shape parameters. And this is for however many samples you decide to put in from the start. Now, if you cast your mind back to webinar number 1, this is the code I gave you, and I did it deliberately. It's not perfect, and we'll show why. The first couple of issues is that I was using not the log likelihood function, but the likelihood function itself, which has its inherent instabilities. Wherever possible, we convert it to a log likelihood. The first random guess at where we started was simply 1, 1. I didn't put any thought into trying to find the trying to find the general location of that likelihood surface. And there is no inputs for the width of our rectangles of guess. So the algorithm defaults to its default settings. So I used this code initially because I wanted to convey how simple it was to actually make this happen. I wanted people to see that in principle, we have a likelihood function that drives everything. But now, knowing what you know, always in practice, use the log likelihood function. And now we've got our bunch of samples. We can go back to, for example, our Weibull probability plot, and then plot lines which represent individual Weibull distributions for each parameter pair. And we can do this over and over again and get this set of Weibull distributions, which then allows us to use those samples for good. So for example, if we want to convert those samples into a sample set of failure probabilities at 2 years, this is the code we use. Now, every different decision scenario is going to require a different implementation of these samples. So in this case, we're creating a sample set of failure probabilities at 2 years. It's up to you to work out what it is you need to do to harness the information in those samples. In this case, we've got a bunch of samples which contain failure probability estimates at 2 years. Go back to our Weibull probability plot. And if we plot these samples, you can see that we now create a bunch of different representative point estimates of failure probabilities at 2 years. That's, in this case, it's only 100 samples for clarity. I think I used 10,000 or something, a much larger number to try and get the histograms we're about to see. Because when we get these samples, we create this distribution of our understanding of the failure probability, and we can plot this distribution on axes which are a little bit easier to see. And now, having gone through that process, here is our understanding of the likely values of warranty period failure. We know that warranty costs in this case is a probability of failure multiplied by the cost of remedying that failure. So the warranty cost itself becomes a set of sampled points, which we then can also put on our axes to give us a distribution of potential warranty costs given our per unit, I should say. And profit, because there's a $10 profit margin in each unit, again, it can be sampled in the same way. And when we plot these profits on a set of axes, we now have that decision actionable information that we talked about at the very start of the webinar, which tells us that in this case, there's a 40.73% chance of a loss. We expect to make a 32-cent profit. So I'm going to take a quick break, get some water into my mouth, and ask open the floor for any questions about what it is we just covered, and if there's any need for me to go over steps in greater detail. Remembering that the equations and the code are in the handouts that Fred has just given some directions to find. Any questions, comments, doubtful points, queries, opinions? Very interesting. Thank you, Michael. Not many people say Markov chain Monte Carlo simulation is very interesting, but I'm glad that I was able to put it in a way that made you think it was interesting. Fantastic. Thank you very much. Any more questions, opinions, queries, doubtful points, ideas, sentiments, emotions? Okay. All right, so what is next? What is the thing we need to do next? Well, I'm done. I did a series of 4 webinars on this topic. So this will be the last webinar in that series. And then of course, there are more things you can learn about Markov chain Monte Carlo simulation. We just looked at an example where we're trying to make a decision based on one random variable. What if you need to combine failure probability with some other random variable which you need to understand in a similar process? Perhaps you need to get some estimates on market share, and you create through Markov chain Monte Carlo simulation, the exact same approach we went through, a bunch of sampled points of anticipated market share for your product. You need to combine that with your failure probability understanding to create decision actionable information for your boss. So there are things you need to consider when you combine 2 random variables that you have sampled in this way to create that decision actionable information curve. There's tons of different things you can learn about, tons of things you can do to take your journey to the next level to make this technique really, really useful. And of course, ideally make you appear uniquely valuable to your managers and your bosses. So I see a question. These are point estimates. Can they be confident, confidence interval bounds? I disagree with your premise that these are point estimates. And I'd go back to this curve here. There is nothing point estimate about that. By definition, we have a distribution being assigned to possible profit values for each device we're investigating. Based on this distribution, we can say there is a 40.73% probability of a loss. Again, this is something you can't say if you're simply dealing with point estimates. We can say things like there is an expected profit of 32 cents, which is essentially the mean value of these candidate profit amounts per unit. So what you can do, again, this is outside the scope of these webinars, is take this this distribution, or even simpler, the histogram on which this distribution is based, and find the 5th and 95th percentiles of this histogram. There's your confidence bounds. So by definition, we want to steer away from point estimates, and nothing we have done today suggests this is all about point estimates. In fact, we've gone to great lengths to make sure that we provide decision actionable information, which includes all the risk-based elements of that decision. From Evan, can you supply representative data sets with the handouts for us to practice using R? Probably not at this stage. It's a simple calculus regarding my spare capacity to continue this group discussion. I would be interested perhaps in seeing if there's appetite for this to be turned into a formal course, where that would then be something that would, if I turn into a formal course, it'd be much easier for me to create these exams and quizzes and scenarios and give you feedback about how you're going. But for webinars, I'll probably struggle to fit it in today, or fit it in as part of this effort. But if there is interest in me turning this into a formal course, to help teach people how to do this in an ongoing way, please let me know. I am thinking about doing it. If it's something that makes sense to you, please let me know. From Simon, is it possible to find out what the mathematics of the MATLAB R sampling algorithms are, or do they remain more or less black box? The answer is absolutely yes, it is possible. In fact, the MATLAB algorithm is pretty good at being open about how it goes about it. It references a paper which describes the algorithmic approach, and you can simply search for the slice sampling algorithm file on your on your hard drive and open it up in MATLAB editor to be able to see how they go about doing it. So it's not a black box by any stretch. The weakness I have with the algorithm is the one I told you about, where it collapses that rectangle in a way that might slice off might miss that slice. So Chris's algorithm is all about those contours and pre-populating or pre-estimating those rectangles, which again speeds up the algorithm and make sure we don't miss anything. Okay, so Peter, is it correct that this method works and the data covers the warranty period? If the warranty period was, say, 5 years beyond the latest time to failure, then you would need to obtain parametric estimates of eta and beta to estimate the future probability of failure by extrapolation. All right, so the answer is yes, 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 and yes. So if we go back to what the underlying mechanics were all about, if we look at the sample parameters create a family or posse of candidate viable probability distributions. Now, as a rule, we don't have the time to test things for years upon years, which means that, as you point out, Peter, we might not have a data set which has failures extending up to our warranty period. So in this scenario, obviously we have lots of data here. But we can still estimate, for example, the warranty period at 100 years, hypothetically, because the viable distributions will obviously extend beyond the range of our data. And the good thing about this approach is that the inherent inaccuracies of us extrapolating beyond our data set are reflected in the way Markov chain Monte Carlo simulation works. The confidence bounds really go out outside the range of our data. The other problem with extrapolation is that we need to be confident that the underlying model still represents the dominant failure mechanisms. So regardless, I picked 2 years here because it's a warranty period, but I could use this approach to estimate failure probability at 0.1 of a year, 2 years, 3 years, 5 years, 100 years, 1,000 years, some of which are outside the range of our data quite happily, at least statistically quite happily. So you could use this approach, at least statistically, for any time period you're interested in. And that this likelihood function, although the examples I showed you today are all about time to failure, you can create a likelihood function which includes sensor data as well. It's very important to include sensor data. So you can use this approach to estimate failure probability at any interval point in time. The question then becomes, how confident are we in the model extending to that region? Okay. You can see someone suggesting that we can create a random sample of data from a distribution on most software platforms. That's true. I think what people are asking for too is that not only can we have the random data being sampled, but have the decision actionable information, that curve, that decision curve at the other end, to see if we can confirm that our individual approaches, our own coding, gives us the anticipated or expected result. But if you do want to go away and practice, you certainly can, feel free. The next step of having this curve to show if you're right or wrong is the next step that perhaps not be included in the course sometime. Some really good questions coming down range too, so please keep them coming for the next 10 or so minutes. Any more questions? Yes, that's true. That's a good point. So for those who can't see the chat window, Mark suggested that I provide the data that I used for today's discussion. Yeah, so if we go back to some slides that show this data being, sorry, give me 1 second. What Mark is essentially suggesting is that I take, excuse my navigation of my infuriating laptop down here. So this slide here represents the act of gathering data. We've got a bunch of data points which I then use to plot on a Weibull chart, which allowed us to superimpose Weibull distributions and all that good stuff. I can give the individual data points or the values for this data here, which then allows you to go away and try and create your own decision actionable information curve. If it looks like the one I came up with, then fantastic, you're on point. And if not, then maybe I'm not on point. Let me know that I've made a glaring error in my approach to this analysis. One way I try to make sure that I haven't stuffed up is when I create my parameters, my parameter pairs, I always, and I mean always, like creating this plot here, which is simply the bunch of Weibull distributions based on each parameter pair. And as you can see, these distributions seem to pretty closely correlate with the plotted data. And when I do that, it gives me a lot of confidence that I haven't made some stupid error in my underlying analysis. Thank you, Sarah. Feel free to reach out if there's any questions moving forward. I see a question from Kirk. If we had suspensions in the original data, how would these equations have to change, if at all? Well, they'd certainly have to change. And creating a likelihood function was part of webinar number 3. If we go back to the likelihood function creation in this example, yes, it was all based on time to failure and no suspended data. If we look at this chart here, what you can see let's look at the MATLAB's coding on the left-hand side, the very top bit. You can see lots of logarithms and stuff in there. All that is the Weibull distribution PDF expanded into logarithmic terms. What you'd have to do is create similar terms, logarithmic expansions of the CDF and reliability functions of the Weibull distribution, include them and embed them in your likelihood function here to incorporate suspended data. You absolutely have to include suspended and censored data, because if you don't, you're essentially biasing your data set to those that failed early. And you don't want that. You're just throwing information away in a way that biases what information you have left. So you have to include suspended or censored data. Again, how the nuances of creating log likelihood functions with suspended and censored data, you might have to do your own research, or perhaps if I do create that course, we can go into that in greater detail, but the likelihood function does need to change. But once you got your likelihood function done, or your log likelihood function done, the process, the Markov chain process, is exactly the same. Okay, from Ken, will you please touch on how you converted the probability of failure distribution into profit or loss? Again, that's covering some ground in webinars number 1 and 2. But I'll quickly go over it right now. So we know what we're getting here. Sorry, the initial raw output of our statistical analysis was a sample of failure probabilities. So here we have a bunch of sampled failure probabilities which represent the probability of failure during our warranty period, which is 2 years. So we're representing these data points on our chart here, simply where 2 years intersects with all these candidate Weibull distributions. We're able to create that histogram of failure probabilities, and we plot that histogram on axes. This gives us our understanding of the warranty failure probability. Now, we know in this scenario, which I created 3 webinars ago, that when we experience warranty failure, it costs us, the manufacturer, $115. That's the replacement cost. So it costs us $115. So the amount of money we need to spend per unit is simply the probability of that unit failing in the warranty period multiplied by the replacement cost. So the warranty cost is equal to F times 115 in this case. So that's the warranty cost we will be paying for each unit. And we plot that information here. That's the warranty cost per unit. So obviously, that sounds somewhat abstract. The warranty cost per unit will either be $115 or 0. I've got it. But this is it. Look at it this way: if we were to have 100 units, then you would expect to be paying around about $1,000 in warranty costs based on this curve here, because this is a warranty cost per unit. The reason we're doing it per unit is it allows us to scale it to the number of units we have sold. And we know in this scenario, which I painted, that when we sell each one of our things, we have a $10 profit margin. So profit is equal to $10 minus the warranty cost. So we have a bunch of sampled profit points, and then we are able to then plot that histogram on this curve, on these axes, and create this decision actionable information here. Now, one of the things our decision maker can do is to increase the retail price. So the profit margin is higher than $10, you'd suggest that the expected profit and the chance of us making a loss on these modem routers is probably too high for us to be comfortable in proceeding with the launch as of right now. So, but that said, if the decision maker wants to increase the recommended retail price by a certain amount to mitigate this risk, that's fine. Now we know, but we can quickly go and work out what effect that will have on this curve to give him or her the confidence he or she needs to press play and launch the product. But again, if you need to look at it in greater detail, please review some of our earlier webinars. And if you do that and there's still questions, please feel free to reach out. Okay, so Fred, I've got access to the Q&A too, so I can look at that. So Srivatsan has asked, how important is it to visualize the slice and the cone you demonstrated? Technically, it's not important. You don't need to. I always like doing it. I always like doing some sort of formal visualization again to make sure that the underlying analysis was in the ballpark. So the visualization I will do personally as a minimum. Again, if my computer allows me to do this, why can't I get you up? So the visualization I will always do as a bare minimum is this one. I'll always plot the sampled Weibull distributions over my plotted data because if there is a correlation, then it's pretty much suggesting that the underlying analysis was correct. But the whole visualizing the slice and cone thing, well, if you're doing 100,000 samples, which is not unusual, you're not going to visualize every single cone and every single slice. I was only doing that to illustrate the mechanics of the algorithm, but I wouldn't do that. Wouldn't do that as a rule. So the question, Srivatsan also asked, what software did I use? I use MATLAB. One of the reasons I use MATLAB is because there is a level of robustness with the built-in functions, and it's really easy for me to create those cool graphics that I can put in webinars and rotate those graphics and otherwise create very useful illustrations that hopefully convey a message in a much more effective way than me just talking. Any more questions? Thank you, Srivatsan, very much. Thank you for your feedback. Thank you, Evan. So it's 12 o'clock now. If there are any further questions, please put them through or ask them right now. But if there's not, hey team, it's been emotional. It's been fantastic. 4 months of talking about Markov chain Monte Carlo simulation. And the historical problems with this are that it's usually embedded in textbooks, which are described in painfully archaic ways, and there's no real drive. It would appear by university professors to make these techniques understandable to the masses. So hopefully this has gone some way to make this really powerful data analysis technique something you would at least feel comfortable in trying. This far and away exceeds every single software package out there. The assumptions that software packages make these days is just mind-boggling, and they get away with it because no one knows the inaccuracies of the outputs of these software packages. They're just assumed to be correct. But especially if you have limited data, you want to extrapolate, like one of our people suggested earlier today. This is the way to go. If there's any further questions, please feel free to reach out. And I think Andre's asking me if I'm going to hold a formal course on this. I think I will. I think I might do it, have it ready to go sometime next year. And if that's the case, we'll probably let you guys know through Ascendo. If you have any point, if I am going to do a formal, if you are interested, or if you're not interested and you've got some ideas about what should be in the formal course, it'd be fantastic to reach out to me and or Fred to let us know what you think should be in it, and I'll do my level best to cover off as many student requirements as possible. Thank you, Mark. So as we're wrapping up, I'm going to leave it on the most important slide, which is, no, not that one. Go and turn data into information.